Does anyone remember what exponential functions are? Good. The variable is going to be on the exponent. Cool. So they're going to look something like this. So f of x equals to a to a power of x. Cool. Where a has to be an element of the real numbers. Cool. A also cannot equal to 1. Why? Can anybody tell me why? Because it would always be 1, right? If you do 1 to a power, 1 to what to every single power is always going to give you 1, right? So it's just going to give you a constant. Okay. So the exponent would be a variable this time. Okay. Now this is what we call a transcendental function. Okay. Transcendental functions are functions that do not deal with algebraic operations such as addition, subtraction, multiplication, or division. Those will be like polynomials, which we studied in chapter 2, or rational functions, which we also studied in chapter 2. So starting chapter 3, transcendental functions are basically what we call non-algebraic functions. Okay? And this is one example of them. We have an exponential function. The other one that we'll talk about today is called a logarithm function, which is also a transcendental function. And then later on in the year, once we start our unit on trigonometry, all our trigonometric functions are also called transcendental functions. Cool? All right. So let's go ahead and begin by figuring out what they look like graphically. Okay? So let's say that I have f of x equals 2 to the x power, and I want to graph this function. Okay? So I'm going to just very quickly build myself an x and y axis. And I'm going to resort to my basically skills from Algebra 1 to help me come up with a graph. Okay? Which is the very first time you learn how to graph is to plot points. Yes? Okay, so this shouldn't be too bad. That's why I picked 2 as a base. Okay? So let's say I go by 1, 2, 3, 4, 5, 6, negative 1, negative 2, negative 3, negative 4, negative 5. And I'm going to go by 2's on the y-axis, so 2, 4, 6, 8, 10. All right, so what's 2 to the first power? 2. Great. 2 to the second power? 4. 2 to the third is 8. 2 to the fourth is 16. 32, 64, and so on, right? So this begins to grow very rapidly. Okay, so it starts going on that direction. What's 2 to the 0 power? 1. So it'll be about right there. Then what's 2 to the negative 1 power? So 2 to the negative 1 power is the same thing as 1 over 2. So it's be 1/2. What's 2 to the negative 2 power? 1 over 2 squared, which is equal to 1/4. And then one last one, 2 to the negative 3rd power will be 1 over 2 to the 3, which is 1/8. What do you notice? It's getting smaller and smaller and smaller. It's approaching 0. Very good. Question, will I ever get a negative number out of a, like if I do 2 to the negative 100, will I ever get a negative? No, it's always going to be very, very small, right? So you said a keyword, it's approaching 0. So when you hear the word approaching a certain value, you should think of what is happening on that graph. What's present? An asymptote. Specifically an asymptote, we're going to have an asymptote here at 0. So it's going to be horizontal. Yes? Okay. So let's talk about a few things about the graph. Okay. So what's the domain of this graph? What's the range? What's the x-intercept? What's the y-intercept? And then if we have an asymptote. Okay, so domain, what do we see? It's going to be all real numbers. What about the range? 0 to infinity, very good. X-intercepts? None. Y-intercept? So 0, 1. Asymptote? Y equals 0, very good. And then lastly, I'm going to ask you something and see if you know what it means. Is this function decreasing or increasing? Do we know what that means? It's increasing. Does anyone know what it means to be increasing? As you go, like as the x values get bigger, do the y values get bigger. That's what it means to be increasing. Decreasing would be as the x values get bigger, the y values get smaller. Okay, that's what decreasing means. So in this case, we have an increasing function. Okay, question: what would happen if I switch this to 10? Would the function still have all real numbers as a domain? Would it still be a range of 0 to infinity? Would it still have no x-intercepts? Would the y-intercept be the same? Would it still have an asymptote of y equals 0? And would it still be increasing? So in other words, I just picked an example with a low number to help you out, but this is the parent function. No matter what number you have in there, it's going to have the exact same domain, range, x-intercept, y-intercept, etc., etc. The same characteristics. Okay? Question. So I want you to think this through as a pre-AP class. Is it possible for me to have a parent function, but instead of increasing, to have it decreasing? How? Make it a negative? Make what a negative? Make A a negative? Okay, let's talk this through, and we will talk about transformations in a second. What does having a negative in the front of a function do? It reflects it over what? The x-axis. So if I put a negative there, what's going to happen is, I'm going to write over this, it's just going to go and look like that, right? Oh, sorry, it's hard to see, but it's going to look something like that, right? There you go. You know, I mean, I agree with you, that is decreasing, right? Cool. But you did a transformation to that. You guys with me? So my question was more like, without a transformation, okay, is it possible to have a parent function that would be decreasing? No? Let me give you a hint. What happens when I switch this number, right? So you said if I kept, like if I did 10, it would still stay the same, right? If I do 100, would it still stay like the same? Like would it still be increasing? If I do 1.5, what if I do 1/2? So f of x equals 1/2 to the x power. Would that still increase? No. Why? Good. When I put the power to be higher and higher and higher, this is not going to get bigger. This is going to get smaller, right? And we can do this very quickly. We can prove this very quickly. So 1/2 to the first power is going to be 1/2. 1/2 to the second power would be 1/4, 1/8, 1/16, and so on, right? What's 1/2 to the 0 power? 1. So then this thing looks like that. But here's my question. I mean, this could still be considered a parent function. Are you guys with me? And that's the thing about the exponential functions. There isn't one parent function. It's as long as you don't have transformations, this number can be basically anything between 0 and infinity. It cannot be 1, right? Cool. The moment I throw a negative in front, it's an actual transformation, right? Okay. So this time, is the domain, the range, is everything the same as my previous function? So is the domain still all real numbers? Is the range still 0 to infinity? I still don't have an x-intercept, right? Y-intercept, I have it at 1, right? But we only... So it is possible for you to exponent function that is increasing or decreasing just as a parent function, okay? So let's make a conclusion. How would I be able to get a decreasing parent function? If a is what? A would have to be less than 1, but greater than 0 for it to be decreasing, okay? And for it to be increasing, what would need to happen? Above 1. Cool. So let's go back to this one. To be increasing, a would have to be bigger than 1. Cool? Which then leads us to our next topic, which is like we can do transformations to this thing. Okay? Now, keep in mind, this is a review of material that you've seen, so this is not going to be like I'm going to go super in detail with stuff, okay? If you have questions, please make sure that you do ask, but this should not be the first time that you see a transformation happen on a function, okay? So, let's review together. So, transformations. What transformations do you remember, like, in general? Okay, so we can have reflections, like vertical reflections. What else could we have? I'm sorry? Okay, I can move up and down. What else? I can move left and right. I can stretch, I can compress horizontally, vertically. And then the last one is I can reflect left and right. Right? If I can go up and down, I could also reflect left and right. So at this point, you should know all of those all of those transformations and how to find them, but let's review, okay? So let's say that you have a function, and that function is just a to the x, right? That's what we have, right? We're dealing with the parent function of an exponential. So let's talk about transformations, okay? What would I have to do to this in order to get a reflection over the x-axis? So a negative in the front. Cool? What would I have to do to this function so that I can have a vertical stretch? I would have to multiply it by a number. And what that number is actually matters. So how would I know if it's a vertical stretch? Very good. So I'm going to choose a random number, and that number I'm going to call it b. Okay? All right. So let's talk about it. So right here you said that is going to be a reflection over the x-axis. Okay. Now if I multiply it by some number b, it can either be a stretch vertically or a compression. It all depends on what that number is. Okay? So Stella said that it is going to be a stretch if the value is bigger than 1. Cool? So by default, what would make it a compression? If it's 1/2, if it's 1/3, so in other words, if it's what? Less than 1 but greater than 0. We don't care about negatives because what does a negative do? It reflects, right? So we only care about the actual value. Okay, so now I have to multiply, right? So I have a to the x, right? Cool. How could I achieve a horizontal compression or stretch? If you multiply, it is going to be on the inside, but at a very specific spot for this type of function. Where your x is, which in this case would be where the power is. Cool? So you would have to multiply by a number. So I'm going to call that number, I don't know, c. Okay? All right. Now, the c value right here can do two things. It can either do a horizontal stretch or a horizontal compression. Does anyone remember how to tell which one to switch? If c is what, it would be a stretch. Less than 1 but greater than 0. And a compression is if c is greater than 1. Okay? So then here's my question then. What would happen if I have a negative in front? Good. A negative would get you a reflection over y-axis. And as you can see, this can get overwhelming really quick. Okay? So a negative all the way in the front is over x. A negative on the exponent is over y. Multiplying by a number all the way in front is going to be either a vertical stretch or a compression. Multiplying by a number on the power is going to give you a horizontal stretch or a horizontal compression. Cool? How do I move left or right? Cool. So you add or subtract on the inside. So in this case, because we're dealing with an exponential, you would either add or subtract a number inside the exponent. So in this case, I'm going to use that with the variable d. So what happens if it's negative d? It goes to the right d units. And if it's positive d, it will go to the left d units. Cool? Which leaves us with our last type of transformations, which would be what? Up or down. So how do I move up or down? You add or subtract a number on the outside. So I'm going to call it plus or minus e. Cool? So e, if it's positive e, what does it do? Up e units. If it's negative e, it would go down e units. And by the way, isn't this true for any type of function? It doesn't matter that I'm doing exponentials. Like I could be talking about polynomials, I could be talking about logarithms. It doesn't matter what I'm talking about. These are the transformations that would occur to any type of function. Okay? All right. We need a minute to write all that down? Yeah. All right. So go ahead and write it down. Okay. So let's go ahead and then do some examples and see if you guys can identify the transformations. Okay? All right. So, identify the transformations. Okay, so let's say that we have f of x is equal to negative 2 times 3 to the 2x plus 1 minus 3. Okay? Oops, sorry. So f of x equals to negative 2 times 3 to the 2 times x plus 1 minus 3. So right now we're not graphing. All I'm asking you is can you identify the transformations? Okay? We will graph some, just not with that many transformations to be honest. Okay? All right. So, what do we know? What do we see? Okay, so we got a reflection over not the y-axis, it's going to be the x-axis. Okay, so remember, when it's all the way in the front, it's going to be x-axis. Okay? All right, what else do we have? We're going to go down 3 units. Okay, so basically that's taken care of, that's taken care of. What else? Stretch vertically. Is that what you said? Okay, stretched. So vertically stretched by how much? By 2. Okay? What else? So that's taken care of. Horizontal compression by 2. Cool. And that would be that number right there. And what else is happening? Almost. Remember, you're going to do the opposite of what you see here, so it's going to be left. Cool. So it's going to be left 1 unit. And I think that takes care of all the transformations, right? Cool. Be careful. A lot of people look at this 3 and they're like, oh, that's going to be a horizontal compression by 3. What is the 3? 3 is your a value, which, by the way, I forgot to tell you. That's called the base. That's the base of the exponential function. So the 3 is not a transformation. That is your actual base of your exponential function. So this right here is the base of your exponential function, which means it does not cause a transformation. Cool? All right, any questions about this? Yes, sir.
If you have a vertical stretch and a horizontal compression, would when you graph them, would they cancel out or something?
Very good, and I was going to ask you guys about that. Okay, so in this, I did this on purpose. So think this through. If you're going to vertically stretch something by 2 units, but then horizontally compress it by 2 units, don't they kind of just undo each other? Whatever you stretched out by compressing it now, the same amount, it's going to just go away. Cool? So it's not like you can just cancel it, right? You can't just be like, let me cancel it here, right? That is what the function is. But if you were to graph it, what that means is that really those transformations just kind of undid each other. Cool? Now, will that always happen? Not necessarily, right? If those numbers are different, then at that point, then definitely they don't cancel out. But in this case, then I totally agree. Cool? All right. Questions about transformations, guys? I mean, because we can sit here and do example and example and example, but honestly, that's what your web assign is for. Okay? Are we good? All right. So then, can we graph? Okay? You ready? So I'm going to give you a graph. And we're going to use we're not going to use a calculator, right? So it's graphing by hand. Okay? I'm going to give you a function, but we're going to do a function that doesn't have so many transformations. Okay? To me, I mean, can you do that? Sure, but it's just way too much, honestly, the one we did above. Okay? So let's say, I don't know, let's do 1/2 2 to the power of x plus 1 minus 1. Okay, what do you guys suggest to do in order to graph this? Yeah, but how? Yes, sir.
What, like, moving up and down, and like the functions first?
Okay, totally agree with you. So I would use, first, in this case, since I know I'm dealing with an exponential function, what I suggest you do is, you got to know where your asymptote is on the parent function. Yes? So on the parent function, you have an asymptote where for an exponential? Y equals 0. Okay, so then ask yourself, this would stretch it, right? Stretching means, this would compress it. Vertical, right? Compressing 0, can you get smaller than 0? No, right? So that's not going to affect it, right? What does this do transformation-wise, this one? Left or right, right? So in this case, it's left. Would moving it left really matter? No. Which then leads you lastly to this, which is -1, which means it's going to do what? So does it actually matter? Yes, it does. So that's where I would start. I would start out with my asymptote. So that means that instead of having an asymptote at y equals 0, I have an asymptote at y equals -1. And I got to be honest with you, it's an exponential. You could just try to use the parent function and then just do the transformations, but you can just plot some points. Because you guys know how to deal with powers, I hope, right? So I'm going to ask you for 3 good points. That's what I'm going to ask you for, okay? So I'm going to make a little table here on the side. And then I want you to think about what would be some good values to figure out, okay? So what would be a good x value to try? 1. Okay, so if you plug in 1, 1 plus 1 is 2. 2 to the power of 2 is 4. Times 1/2 minus 1. So that means that you have the point 1, 1. Are we okay with that? 1, 1. Okay. What else do you want to try? I'm sorry? -1. Okay, -1. Okay, what's -1 plus 1? 0. What's 2 to the power of 0? 1. Okay, 1 times 1/2? 1/2. Minus 1? -1/2. So you have the point -1, -1/2. So that'll be about right there. And let's do one more. 0? Okay. 0 plus 1 is 1. 2 to the power of 1 is 2. 2 times 1/2 is 1. 1 minus 1 is 0. Now, do you know what it looks like, or do you need more points? We know what the parent function looks like, so we're going to use that to help us, but I have a very good feeling this thing is going to look like that. Because that's what our exponential looks like, right? We don't have any reflections, right? So it should look that way, right? Especially because we know our a value is greater than 1. It should be increasing. Cool? So, what are you going to do to graph exponential functions? Before you plot points, figure out where your asymptote is, and then just plot some points. I am not going to stop you, and if you want to do this, there are some of you guys that, if you want to memorize what the parent function looks like, and then do the transformations to that, and then do it yourself, you're more than welcome to do it, okay? I personally just believe, just mathematically speaking, that making a table for an exponential, it's a little easier in my opinion, okay? All right. Questions about graphing exponential functions? All right. 2 to the power of 0, 1. What do you guys think? 2 to the power of 0. Why is it 1? But why? That's a good question. I mean, you guys have been trained to say that. So why is anything to the power of 0, 1? You're right. Okay, think about it. A power is how many times you do something, right? So like 2 to the power of 2 is 2 times 2, right? And 2 to the power of 1 is 2. 2 to the power of 3 is 2 times 2 times 2. So 2 to the power of 0 is like you have nothing, right? So your question is like, why is it 1? It's because you have to, like, think about it. It's like the amount of times you have. So you have 1 time because you have nothing. So you have to have something. It's kind of like, you have to think of it of, this gets a little bit of statistics, but do you guys know combinations? Like, how many ways can you arrange that? Well, just be one way. You with me? Okay. But it is a good question. A lot of you guys, like all of you guys were like, well, because anything to the power of 0 is 1. Okay? There's a reason for it. Cool? All right. Are we good so far? Okay. So now, the last thing I want to talk about as far as exponential functions go, well, actually, there's 2 more things. Is I want to make sure that you can use your calculator with exponential functions, which is, can you evaluate functions? So evaluating functions. So just to keep it simple, let's say you have f of x equals 2 to the 2x plus 1. Cool? All right. And if I ask you to evaluate at x equals 0, what would you do? Input 0. So this would be f of 0 is equal to 2 to what power? 1, which is equal to 2. Right? So that's easy. Right? But then this is where it gets tricky. What if I ask you to evaluate it at 2.1? Well, that's going to be what? F of 2.1 is equal to 2 to the power of 2 times 2.1 plus 1, right? Which in that case, what? 2.1 times 2 is going to be 4.2, right? Plus 1 is 5.2, so that's going to be 2 to the power of 5.2. And then at that point, I'm like, well, what do you think? Well, I know that 2 to the power of 5 is 32. So it's got to be bigger than that, right? But what about 5.2? And this is where your calculator is going to come in. So I don't expect you to know how to do this, okay? So I need to make sure that you know how to do this on the calculator, right? So grab your calculator just to make sure that you know how to use it. This shouldn't be a difficult part. So, I mean, you can get to this part, right? So how do you type that in the calculator just to make sure? We don't need a y equals because we're not graphing. Only if we're graphing, okay? So we don't need a y equals. What do I need to do just to figure out what 2 to the 2 what is it? 2 to the 5.2 is? So plug it in. Yes, so what does that mean? So 2, and then there's this little caret right here. That means power. And then 5.2, and then enter. So look, we did expect it to be bigger than 5. Bigger than 32, right? Yes? So 2 to the power of 5.2 is 36 point, I don't know, let's say 8. And then notice how I'm going to answer this question. I'm not going to say equals. I'm going to use this symbol. You guys know what that means? Approximately 36.8. Okay? So now when you use a calculator and you're going to round, do not use the equal sign anymore. You use the approximation sign. Okay? I will tell you both on the quiz and I think on WebAssign what they want you to round into. Okay? Yes, sir.
When you did exponent, so the 2x plus 1, did you have to separate the 2 with like parentheses?
Oh, for transformations? Yes, sir. That's a good question.
So like stuff like this, would you not have to?
No, because I'm just plugging in, right? But I agree with you. So that was a good question, and we can kind of go back real quick to the transformation idea. Let's kind of take a break here and pause. So what he's mentioned is, like, let's say that I had a function like, I don't know. We'll just keep it simple. 2 to the 4x plus 16. And I ask you for the transformations, okay? First, you need to recognize this right here doesn't look exactly like the way we wrote it. Did you guys notice that the way we wrote it had a b value and then in parentheses the c? What that means is you have to first rewrite it as 2 to the power of 4 times x plus 4. because as you can see, you're not going to have a problem identifying, in this case, the compression, right? You see how if I look at both of them, I'm like, it's going to be a compression with 4, right? But notice that if you don't pay attention, you're going to say that this thing moves left 16, when in reality it was moving left 4. So thanks for bringing that up. They should be thankful when they get to the WebAssign. You have to factor out the B value. Cool? But as far as evaluating, not necessary, because it's still going to give you the same number. Cool? All right. Questions about using the calculator to evaluate. Right? I mean, if it's an integer, great. If it's a decimal, I mean, just put a decimal in, right? It's not that bad. Okay? All right. Let's say I give you f of x equals e to the power of 3x minus 1. Okay, so first of all, let's talk about that. What do you remember about that from Algebra 2? It's a what? So it's a number. E is a number, right? Does anyone remember what its name is? Yeah, it's Euler's number, yeah? This is Euler's number, and it's named after the guy that found it. Okay? Does anyone know what it approximately equals? Nope. It's okay. It's 2.718. And then it keeps going on forever because this is an irrational number. Okay? So this is very similar to the idea of pi. Cool. You know when you see pi, that's 3.14-ish. When you see e, it's going to be 2.71-ish. Okay? It is a number. This is also called, it's called Euler's number, but a lot of people call it the natural base. It is called a natural base because it occurs in nature a lot. And we'll get to that in 3.5. Okay? So this number is actually kind of a big deal. Cool? All right. So in other words, when you see this, this is a number. I wouldn't expect you to know how to do it by hand, right? Number one, to graph it. Number two, to evaluate, etc., etc. So if I ask you, like, for example, to find f of 2, well, in this case, you're going to say e to the, well, 3 times 2 is 6, minus 1 is 5, right? Yes? Without a calculator, your answer would be e to the 5. Without a calculator. That's all I expect from you. With a calculator, then I would expect you to figure out what it's equal to. Does anyone know where Euler's number is located on the calculator? Second and what, I'm sorry? Okay, right here, ln, right above it, it would give you the e, so it would give you e to a power. So in this case, we would say e to the power 5, and then hit enter, so it's 148.4. There is another location for e on the calculator. Does anyone know? It also requires for you to hit second, so it's one of those. Yes. It's in the division symbol. So if you look at the division symbol, right here it gives you e. So what's the difference between this one and this one? Well, this one just gives you e, and this one gives you e to a power. Okay? Questions about the natural base? Are we good? Okay, so what I want to close down with this section before we take a break is solving some equations. Okay? Okay, we're going to solve, and I really want to highlight the word simple. So these are going to be easy. There is an entire section in where we're going to solve equations, and those are going to get complicated. But for right now, let's just kind of talk about very simple equations. So equations means we're going to have an equal sign, we're going to have two sides, we're going to be solving for x or whatever variable we're talking about. Okay? So, hypothetically speaking, let's say that we have the following. E to the power of 2x minus 1 is equal to e to the power of 4. So we want to solve for x. And you wouldn't have a calculator for this one. I know we're dealing with e, but you don't need a calculator for this. How would you go about solving this? You said 2x minus 1 equals 4? Why? Because the bases are the same. So remember when we were doing partial fraction decomposition, And one of the parts was like, once we got the the denominator equal to each other, why would we care about the denominator for the rest of the problem? Same idea here with exponentials. If you already have the bases equaling to each other, they really don't matter. Cool? So what's the answer for this? It's going to be 5 over 2, right? We add 1, so it'll be 5, divided by 2 will be 5 halves. Cool? All right, let's try another one. 3 to the power of x minus 5 is equal to 81. Okay, so that first one, it was awesome. We had the same basis. We just had to set the powers equal to each other. This one of them is not even an exponential. Can we make it an exponential? How? Okay, so you're saying that 81 is the same thing as 3 to the power of 3? You guys agree? Cool. So then 3 to the power of x minus 5 is equal to 3 to the power of 3. Are you sure? Because 3 to the power of 2 is 9. 3 to the power of 3 is 27. 3 to the power of 4 is 81. Okay? All right, but now that we got the correct power, what do we do? The exact same thing we just did for the first example. Now we have the same basis. All we care about is the exponents. So what is x? 9. Are we good so far? Okay. Now let's say that I have 1/3 to the power of x is equal to 27. So 1/3 to the power of x is equal to 27. Okay. So there's a pattern here, right? There's like, okay, we should probably try to get same basis, right? Okay. 1/3 is the base of the left-hand side. The right-hand side is not even exponential. So we can try to get 1/3 to a power to get 27. That shouldn't be a problem. Can we do that, or do you guys have another suggestion? Or how do you guys know how do you want to go about this? Well, think about it. How can you get? Because you have a good point. So earlier you said we had a fraction, and then if we put it to higher and higher powers, we would get smaller and smaller numbers. But I want it to get bigger. So what do I need to do? Yes. I need to do to a negative power in order to get this to work. So if I'm going to use the 1/3, is that what you guys want to do? The 1/3. Then I need to do 1/3 to some negative power in order to get a 27. And here's the trick, guys. Forget that it's a fraction. Just ask yourself, 3 to what power gets you 27? So now just do a -3. You with me? Okay, so now that you have the same base, you get what? X equals to -3. All right, for those of you that are like, oh, I don't really think I'm going to be successful with fractions, dude. You're killing me here. Okay, let's go on an alternate route. You should be able to write 1/3 as a different base. And that hopefully is, we all know this from hopefully like Algebra 1-ish, that 1/3 is the same thing as 3 to the power of -1. So I could rewrite it as 3 to the power of -1 to the x is equal to 27. Yes? And then 3 to the power of 3 is 27. What happens when you have a power to a power? You multiply them. So that's going to be 3 to the power of -x, and you see how I get the same answer. -x is equal to 3, which means x is equal to -3. Cool? I'm sorry, this is where, unfortunately, those little rules with exponents come back, and this is where some of you guys begin to struggle because you don't remember those little rules, okay? Please, please, please make sure that you ask me if you get stuck with the rules of exponents, okay? All right. That's going to be it for exponentials. We're going to take a break, and then after lunch, we will talk about logarithms. Cool?